In this lesson, we're looking at a couple of special right triangles. So in this diagram, we have an isosceles right triangle. It says to identify the base angles and use the fact that they are complementary, remember complementary means that they add up to 90, to write an equation relating their measures. The base angles are angles A and B. And if they're complementary, then I know that the measure of angle A plus the measure of angle B equals 90. And then it says use the isosceles triangle theorem to write a different equation relating the base angle measures. Well, remember from, module 5, I think, we saw that isosceles triangles have, we already know, two congruent sides, but we also know they have congruent base angles. So the measure of angle A equals the measure of angle B. And so if we take these two equations together, well, that means that the measure of angle A plus the measure of angle A equals 90. So 2 times the measure of angle A equals 90. Measure of angle A, therefore, is 45. And that's also going to equal the measure of angle B. So what must the measure of the base angles be? 45. Now they want us to use Pythagorean's theorem to find the length of the hypotenuse in terms of the length of each leg, x. Well, we know Pythagorean's theorem says leg squared plus leg squared equals hypotenuse squared. So AB is my hypotenuse squared equals x squared plus x squared. When I combine my like terms, I have that AB squared equals 2. X squared. And if I take the square root of both sides of this equation, then I have that AB equals, well, let's think about what the square root of this is. The square root of 2 is something really unpleasant in my calculator, but the square root of x squared is just x. So AB equals x times the square root of 2. So is it true that if I know one side length of an isosceles right triangle, then we know all the side lengths? Yes. If given a leg, you know the other leg is equal, and the hypotenuse equals leg times radical 2. If you know a hypotenuse, then I hope it would make sense that you'd be going in the opposite direction. If I know the hypotenuse, I would divide it by radical 2, both legs equal hypotenuse divided by radical 2. So in this right triangle, suppose I draw the perpendicular from C to AB. How would I find the length of CD? Well, we already know that the measure of angle B is 45. And if this is 90, then what am I left with? Another 45 degrees. So then I know triangle BDC is an isosceles right triangle. Where 1 is the hypotenuse. So like I said here, the leg, let's say BD, oh no, I'm trying to find CD. CD is going to equal that hypotenuse, which is 1, divided by radical 2. Now, one thing that you need to know from algebra that you either may not have gotten to or you may have forgotten, you're not allowed to have a radical in the denominator of a fraction. So you have to do something that we call rationalizing the denominator. And what we're doing, let me rewrite this so you see a top and a bottom clearly. what you have to do is multiply top and bottom in this instance by radical 2. And we're allowed to do that because radical 2 over radical 2 is just 1. I can multiply by 1 forever. All right? Now, straight across the top, 1 times radical 2 is just radical 2. On the bottom, I have radical 2 times radical 2. That's the square root of 4. You should know that the square root of 4 is 2. Let's consider a different kind of special right triangle. It starts by looking at an equilateral triangle. So I have equilateral triangle ABD, where BC is a perpendicular from B to side AD. They're asking us to determine all of the angle measures in triangle ABC. Well, remember that an equilateral triangle is also equiangular, so the measure of angle A is 60. If BC is perpendicular to AD, then that means that the measure of angle BCA is 90. And we know that the three angles of a triangle have to add up to 180. So when I add 60 plus 90, I get 150. Subtract that away from 180, and the measure of angle ABC is 30. Next thing they're asking us is, why is triangle ABC congruent to triangle DBC? Well, we said earlier that if a triangle is equilateral, then it's also equiangular, so I know angle A is congruent to angle D. I know that this 90-degree angle is also a 90-degree angle here, and segment BC is congruent to itself by reflexive property. Okay, so angle A is congruent to angle D because equilateral triangles are equiangular. Angle BCA is congruent to angle BCD, since all right angles are congruent. Segment BC is congruent to segment BC by reflexive. So the triangles are congruent by angle side. So let's say we make the length of AC x. What then has to be the length of AB? Well, let's come back to this diagram. If AC is x, then because these triangles are congruent in CPCTC, I know this is also x. The length of AD, therefore, would have to be 2x. And since this is an equilateral triangle, AD is congruent to AB, so AB would also be 2x. Okay, so why is it 2x? Once again, AC is congruent to DC. AD equals the length of AC plus the length of CD, which is x plus x, which is 2x. Triangle is equilateral, so I know AB is congruent to AD. And so that's why the length of AB is 2x. And so now, once again, they're asking us to use Pythagorean's theorem to find the missing side of this triangle. So hypotenuse squared equals leg squared plus leg squared. 2x quantity squared is 4x squared. I'm going to get all my x squared stuff together, so I'm subtracting x squared from both sides and getting 3x squared equal to BC squared. And then when I take the square root of both sides, here, very much like here, I can pull the x out of the radical, but the number ends up staying in. So BC equals x radical 3. So then what is the ratio of the side lengths of a right triangle with acute angles measuring 30 and 60? So it's x radical 3, and 2x. Another way that I can think of this is 1 to radical 3 to 2. In this diagram, they're telling us that there's an error. The student drew this triangle and labeled the side lengths as shown. How can we tell that they've made an error, and how do we correct it? Well, remember, the hypotenuse is always the longest side. Now, if my shortest side is 3, we already talked about the hypotenuse being twice that long, so there's nothing wrong with these two sides, but JK is going to equal 3 radical 3, not 6 radical 3. So now we're using these properties, and they've kind of outlined them for us here. We're using these properties to find unknown side lengths. In example 1, part A, I have an isosceles right triangle, also known as a 45, 45, 90. I know the hypotenuse, and I'm trying to find the unknown side length, so that's each of these legs. Now I know that they're equal to each other. I know that the hypotenuse equals each of the legs times radical 2. So I substitute 10 in for what I know, and they're doing something in this text that I've never seen before, but I kind of like it. What they did from here to here is multiply the whole equation by radical 2. Okay, so 10 times radical 2 is just 10 radical 2. When I take this expression, this AC times radical 2, and I multiply it by another radical 2, remember we saw this earlier. Radical 2 times radical 2 is radical 4. You know that the square root of 4 is 2. And then finally, it's very easy to take this equation and divide both sides by 2 and get this value. In part B, this time I have a 30, 60, 90, where I'm given the short leg and I'm trying to find the missing side length. So that's the hypotenuse and the longer leg. Now I know that the hypotenuse is twice as long as the shorter leg. So DE is 2 times EF. Now I'm going to substitute 5 radical 3 in for EF. Now I'm going to multiply the 2 times the 5 and get 10 radical 3. So I know that the shorter leg is radical 3 times as long as the shorter leg. Okay, so that means that DF is that short leg, 5 radical 3, times radical 3. So apparently in the textbook they wanted me to put the EF here. So if it makes your heart happy, you can do this. I don't see any reason to do it. At this point, 5 radical 3 times radical 3. Well, let's think about this. Radical 3 times radical 3 is radical 9. Square root of 9 is 3. So I have 5 times 3, which is 15. And that's the length of DF. A couple more examples like that. Here, I have a 30, 60, 90, and I know the hypotenuse. I know that the hypotenuse equals 2 times the short leg. So my hypotenuse is 4 radical 3. That's going to equal 2 times JK. And so in order to solve for JK, I'm just going to divide both sides by 2. That means JK is 2 radical 3. LJ is my long leg. I know that the long leg equals the short times radical 3. Well, the long leg is LJ. The short leg is this 2 radical 3 I just found. Again, radical 3 times radical 3 is radical 9. What's the square root of 9? It's 3. Times this 2 is 6. So LJ is 6 and JK is 2 radical 3. In this example, notice that it's an isosceles right triangle. That means that the legs are equal. I'm given a leg. That means the other leg is the same thing. So QR is also 2 radical 6. From here, I know that the hypotenuse equals a leg times radical 2. My hypotenuse is PQ. My leg is 2 radical 6 that I'm multiplying by radical 2. So that's 2 radical 12. Something about that 12. It's divisible by 4, which is a perfect square factor. And remember from last module that when we have a radical, we want it to be in simplest radical form. We don't want any perfect square factors hiding inside of it. So this is 2 radical 4 radical 3. But you know what the square root of 4 is? It's 2. Times this 2 is 4. So my hypotenuse is 4 radical 3.